Okay, I think we're going long enough. You have a question, yeah?
So when you're talking about synaptic meaning, obviously it's
right.
Is there a critical point for a neuron in which enough big synapses have been bring to where the neuron is free, or am I confusing something there?
That's a good question. I wouldn't want to be answered for sure because I'm not expert in that, but certainly most of the process we're talking about isn't about neurons disappearing. It's a process of the connections between neurons disappearing and neurons being pruned. So it is true that neurons die, so part of what happens is that some neurons are dying, and there's this question about how much new neurons are actually being born at the same time. But most of the work that's being done is not about whether the neuron is dying or not, it's about how many connections it has. And if you have a neuron and it isn't connected to other neurons, then it's effectively not doing very much in the course of the brain. Yeah? No, as we'll see in a second, synaptogenesis is happening all through life. As long as you're alive and you're thinking and you're learning, synaptogenesis is taking place. And it's worth saying that synaptic pruning is taking place all through life too. So that's happening in babies. So when you see that line, what you're really talking about is how the balance between synaptogenesis and synaptic pruning. So it's how much of what's going on is about proliferating new connections and how much of what's going on is about pruning the connections that you already have. So what you see is that early in life you see lots of synaptogenesis and relatively less synaptic pruning, and then you see that kind of reversing as you get to be older in life. And then when you get to be really old, like after adulthood, then you just don't see as much variation either way. You don't see as much, and then new connections being formed, and you don't see as much pruning. You've got a brain that's pretty much functioning the way it is. Although we'll see in a minute there are some exceptions to that. Yeah? Well, it isn't really about which part of the brain develops first, but different parts of the brain have different profiles about when you have synaptogenesis and when you have pruning. So, for example, the occipital lobe, which is the part of the brain that's involved in vision, seems to be wired up. The synaptogenesis process is over quicker than the frontal lobe, which is the last part of the brain to mature. So, in terms of when the parts of the brain mature, the occipital part, the back, the visual section matures the earliest, then language matures later, and then the prefrontal area is the last one to mature. Okay. So I've been emphasizing the fact that that everything that the brain's designed to be a learning machine, it's designed to respond to experience. People have discriminated between different kinds of ways that the brain responds to experience. And people talk about this as the difference between experience-expectant processes and experience-dependent processes. So one way of thinking about experience-expectant plasticity is that there are some things that basically are going to happen to everybody. So for example, all normal human beings with eyes are going to get visual input. All normal human beings with ears are going to get auditory input. And some parts of the brain seem to depend on that kind of input to be tuned up. And if they don't get that input, then they seize up and they don't work in the way that they're supposed to. So, for example, a very good example is that if you have things going wrong with the visual system in that very, very early period of development, then the visual system may just never wire up properly at all. Some of you may have had the experience with sometimes babies have what's called amblyopia, which means that their eyes don't focus. And if that happens, then you have to put a patch on the babies to actually get the coordination between the two eyes. And the reason why you need to do that is if you don't do that in the early period, when the children are small, then they're never going to be able to coordinate the information from their two eyes and have three-dimensional vision. And the interesting thing is, if you had amblyopia later on in life, if you started out being able to coordinate the two eyes, and then later on, say, you get cataracts, or you get some other problems so your eyes aren't coordinating, then you don't get those kind of long-term effects. So as an adult, for example, if you have cataracts, and you take the cataracts away, then nothing happens to your vision. Your vision's still just as good. Whereas if you have a baby who has cataracts, then even when they correct the cataracts, the baby may still have trouble actually seeing. And we see the same thing in deaf children who are learning to sign or not. So deaf children who get sign language from the time that they're very little develop language skills that are just as sophisticated, just as good as the skills of hearing people. But deaf children who don't get to learn about sign until they're adults, for example, which happens sometimes, never reach the same kind of level of linguistic sophistication that deaf signers who've got sign from the time they're very young get. So even if, say, you started learning sign when you were 12 and you lived to be 70, you wouldn't be as good a signer as someone who was learning sign from the time they were born. So these are examples where what happens in that very early period, what people sometimes call a sensitive period, really shapes what happens later on. And these experience-dependent processes aren't just dependent on those are experience-expectant processes. Experience-dependent processes have to do with the way that our brain changes in response to the very particular experiences that we have, not just sort of whether we get any visual input at all or any sign language at all. What specifically happens to us? What do we learn? What do we practice? What skills do we develop? And that kind of plasticity, as I mentioned before, although it's stronger early in life, continues throughout life. And one of the really lovely dramatic examples of this, so we can show, for example, that practicing a particular skill actually reshapes the brain. So, for example, in studies with monkeys, if you exposed the monkeys to a lot of auditory input, a lot of sounds, but didn't give them very much tactile input, then that auditory part of their brain would actually expand and the tactile part would actually contract, and vice versa. You see this really dramatically in babies, but you can see it even in adults, and you can see it not only in monkeys, but even in human adults. So let me give you a nice example of this. And this is an example that actually comes from taxi drivers in London. So if any of you have ever been in London know, the taxi drivers in London, unlike the taxi drivers in San Francisco, have this incredible knowledge of everything about the London streets. So you can actually, ask a taxi driver in London to take you anywhere in London and they'll know how to do it. And here's a little bit of video about studies about... Oh, come on. Yeah, let's see if we can get out. Okay, let's see if we can just get back to the start. Okay. Working quite succinctly. I think we have to watch a damn ad first now.
Folks who save hundreds of dollars switching to Geico sure are happy. I say
sorry, guys, this is not it.
London's legendary taxi drivers are the Olympic athletes of memory, navigating the intimidating labyrinth that is central London. They must create an intricate mental map consisting of thousands of streets, landmarks, and locations. University of London scientists studying the shape of memory found ideal subjects right in their own backyard. For 150 years, every new cab driver has had to pass a grueling exam, known to Londoners simply as the knowledge. It takes most hopefuls at least 2 years to master, giving researchers a superb opportunity to look at how the brain adapts when required to retain vast amounts of information.
Thanks, mate. Can you take me to the other hall?
When somebody gets in your cab, they'll say, take me to so-and-so, it's got to be like that. You've got to know instantly where you're going, which way to be pointing. So there's a lot of retention. You've got to retain a lot of what you've learned as well.
Scientists suspect that a particular region of the brain called the hippocampus might be the key to the taxi driver's success.
Now, run me to the nearest police station.
If memory depends upon the hippocampus, at the Knowledge Point School, drivers in training surely give this part of their brain a good workout.
Dave, give me the name of a restaurant on Fulton Road, the lady's name. Chuck me mirrors. Hereford Road, where would you give me? Veronica's.
After class, students like Andy Miller take to the streets. Since visual processing occupies more brain activity than all the other senses combined, it is not surprising that direct experience is an essential part of the knowledge training.
You start off learning all the roads, then you have to learn all places on every road.
With all the routes that you have to do for the knowledge, you couldn't possibly do it on the map. You have to get out on your bike in the rain, the cold, the snow. You learn it bit by bit.
But how does the brain retain and order all that information? As the scientists suspected, mastering the knowledge may have a physical impact on the brain itself. Their study concluded that part of the hippocampus was indeed larger than average in these drivers. In fact, the most dramatic differences were seen in the drivers who were on the job the longest.
The hippocampus has a spatial map in it, and what seems to be happening in the taxi drivers is that the spatial map is laid down of central London, and laying this down causes the connections to develop and grow and more of them to form, and that makes the part of the hippocampus get bigger.
It's almost like you've somehow, somewhere up in your brain, you've created enough space to sort of slip this map in, a little bit of software.
This study suggests that the adult brain can refashion its basic anatomy according to the requirements of its owner. Doctors hope these insights can be used to help restore the minds of stroke victims, Alzheimer's patients, and those suffering brain traumas.
Okay. So I should add that in those studies, one of the other things that they found, which was really most dramatic, was when they looked at the size of the hippocampus before and after the taxi drivers were learning the knowledge, they saw that the hippocampus literally just got bigger after the drivers had learned all the things that they needed to learn. And remember, the hippocampus is a part of the brain that has neurogenesis, where there are actually new neurons being formed, as well as a part of the brain that's involved in synaptogenesis. So that's a really dramatic example of the way that very specific kinds of experience can end up having a big effect on the physical size of the brain, actually what's there in the brain, as well as having an effect on the connections between the brain, which we don't have to be there. I think we'll skip the explanation break because we're running late. So let me just mention the last thing, which is that issue about plasticity also affects the way that children recover from brain damage. So in general, the picture is that early damage is much, much, much less damaging than later damage. So there are examples, for instance, of children who have a condition called hydrocephaly, which means that there's a great deal of fluid in their brain. And children can end up with just a quarter of an inch of cortex around this central mass of fluid. And often, as you might imagine, this leads to a mental retardation. But some children with hydrocephaly, with these very, very thin cortices, seem to develop perfectly fine and can use that tiny part of cortex to even go to college and function and learn the way that typically developing children can do. So the general picture is that parts of the brain, since the brain is so much more flexible and plastic early on in development, some parts will take over from other parts. And the same damage, say a stroke, that in an adult would lead to, say, the complete loss of language or really serious damage, the same damage in children is recovered from much more quickly. But it turns out that actually, although you don't see the same kinds of large damage in children that you see in adults, there are more subtle effects. And sometimes those effects don't show up until later. So for example, if you looked at children who had a congenital lesion in a particular part of the brain, by the time they were 6, they seemed to have completely recovered. But when they were measured again in adolescence, it turned out that they were having more trouble with some language tasks and other tasks than typically developing children were. And a lot of what seems to happen is that the brain's very good at adapting. And the young brain, again, this makes sense with this general picture of plasticity and learning, the young brain's better at figuring out ways to, say, bypass problems than the old brain is. So part of the reason why we may be seeing children with brain damage apparently doing so well is they figured out ways to solve the same problems by other means. And if you put them in a situation in which there's only one way to solve the problem, then you see that there actually is damage there. But I think the general take-home message of all of this is that the brain in general is this incredibly plastic and flexible system, and that the brains of children in particular are plastic and flexible and changeable and sensitive to experience in a really dramatic way that makes them even more true than it is for adults. So one of the ways that I describe this sometimes is that I say we sometimes think about children as if they're defective grown-ups, but a better way of thinking about it is that we're like two different stages of the same creature, like caterpillars and butterflies. So they have a brain that's really well designed to do the things that they're good at doing, and we have a brain that's really well designed to do the things that we're good at doing. Except that it's actually kind of more like they're the butterflies who get to flit around and experience new things and go around from flower to flower, and we're the caterpillars that are going along that little narrow, functional, goal-directed, focused adult path. Okay, so let me stop there and we'll talk some more next time.